Cristiana Ferreira is currently at the Federal University of Porto, Peru. That's how I know it, Peru. She obtained a PhD from the same department in 2009, where she was working in collaboration with Bristol, where she spent some time and where I knew her. Her research expertise is really into measuring the small strain stiffness of soil with seismic waves. Since then, she's been involved in a large number of projects. One, she's going to be including non-standard soils, and I think that is something that she's going to talk about today by telling us the importance of looking at the undisturbed soil response as well as the reconstituted one. So, Cristiana, thank you.
Thank you. Good afternoon. I'll try to make this short and end it early. And so I'll talk about the soil liquefaction assessment in undisturbed and reconstituted conditions and the challenges and opportunity that this research has provided. And for me, it's an honor to be here. Thank you for the invitation by Professor Kinchi and by the TC101. And this is the work of a number of people from the University of Porto that I'll acknowledge in the end. So this is just the outline of the presentation. I'll start with the motivation. So Portugal has historical evidence of earthquake-induced liquefaction, and this started, or there's records of it, since the big earthquake of 1755 in Lisbon. And there are evidences of liquefaction occurring associated with the big earthquake, and also in the 20th century in the region of Lisbon, but especially in Benavente, where there were sand boils observed and other clear evidences of liquefaction. There is a map from 1993 which indicates that the area surrounding Lisbon has widespread liquefaction potential, and this is the area that we were aiming to look and to study. And this came together with the opportunity to work with other universities and partners, industry partners throughout Europe, and especially the development of a new proposal of a liquefaction hazard map in Europe within the Liquefact projects. And it involved different countries, and especially 4 countries where experimental sites on liquefaction were studied, namely in Turkey, in Slovenia, in Italy, and in Portugal. So I'll talk about the pilot site. So this is an area just outside of Lisbon, east of Lisbon, and involves a large farming region and some mid-sized cities. So we started by collecting existing data from the geotechnical report, and there's a lot of information from the construction of a motorway and a long bridge and viaduct. And this covered a very large area and involved, just by collecting the existing data, a numerous number of boreholes, field tests, including geophysical results as well. And from this data, we started to prepare the topographic and geological model, and we identified the areas with extensive and thick layers of sand at loose and saturated conditions, therefore prone to liquefaction. And this is just to show the variability of the area. Obviously, it's a very wide area, but it is mainly constituted by sedimentary deposits with loose to medium sandy and silty sandy soils. But these are interbedded with soft fine soils, which are one of the key aspects of this research. So the site investigation following the collection of existing data was spread out in the pilot area and involved a considerable amount of testing, of field testing, and also the collection of high quality samples. And this is a relatively new opportunity that we have here to collect samples in loose, saturated, and sands. So something that's known to be hard and challenging in geotechnical engineering. So in this site investigation campaign, we carried out a number of SPTs, not many, we prefer the CPTs. And so we analyzed the CPTs in terms of the properties, and we identified the areas where we had predominancy of sands. But we did also DMTs, a lot of geophysical tests, and this allowed us to identify the lithology of the soil, the stress strain properties, the soil behavior type. They identify the soil stiffness, ES, if you like, before sampling, and also to study, based on field tests, the liquefaction susceptibility using different methods. We've seen this before, and basically we use the most recent proposals for assessing liquefaction from SPT, CPT, and DMT, and also from the shear wave velocities that I'm not addressing here. Following this characterization, we moved to the advanced sampling techniques, and in the same model that you've seen before, we selected the sampling experimental site in one of the corners of the site, where we had easy access and an interesting distribution of liquefier soils. And when we did the first SPT tests, we could see clearly that there was an interbedded, or if you want, intercalated layers of sands and silts. You can see those laminations. Obviously, this is a SPT test, so it is just not good for laboratory testing, obviously, but it shows how the soil is in depth. And this was very useful to complement the information from the CPT tests in order to select the most relevant depths for the sampling. And obviously, this interlay would require a correction for the presence of fines that we could see here and that were not easily identified in some of the tests, especially on the SPT. So what we did was collect these the soil from the SPT sampler and conduct laboratory tests to identify the grain size distribution and, more importantly, the percentage of fines, and also the plasticity index, and then we use the correlations for CPT and DMT. Following that analysis, we selected the sampling depths in order to have the most susceptible to liquefaction, to make sure that these were collected. And for this purpose of the advanced sampling stage, we selected 3 samplers. One that is more commonly used in Portugal, the Mansfield sampler, then the Dames and Moore sampler, and the gel push sampler. Very quickly, I will introduce this sampler. So this is a rotary track triple tube with a PVC liner, but it uses pumped water, so it can affect the water content and sometimes wash some of the material, but it's very robust and it can go through even harder soils. Then the Dames and Moore is basically an adaptation of the Osterberg type sampler, but it uses a smooth brass liner, which is very helpful in reducing the friction between the soil and the liner. And the other important aspect of this sampler is that it uses a neoprene seal in order to create vacuum when we're sampling and retrieving the sampler, which is very beneficial in reducing the risk of the sample falling. And this is particularly important when we are dealing with loose sands. And you can see here a bit more detail, an example of the collected sample and the sleeve which is located at the bottom of the sample. The third sampler is a relatively recent sampler and is called the gel push. It was developed in Japan and is also a hydraulic fixed piston sampler, but it uses a viscous polymer gel, which is very effective in reducing the friction between the soil and the liner. It also has a core catcher similar to the Mazier, but it's definitely the most advanced technique and the one that requires more specialized personnel because it is much harder to work. So you can see here an example. You can see here how the polymer is coming off the sample at the end. And so the trick of the success of this sampler is really the use of this polymer solution, this gel, which is has extremely low viscosity, but it's also very hard to prepare in situ. So sometimes we observe that it's hard to do the sampling at a particular depth because the gel wasn't so carefully prepared, and we always had to prepare it every time at each depth. And at the end, so after sampling, you can see here the core catcher, which is closed. So it initially was open, so we didn't see it. And at the end, it closes with some metallic pressure that's applied at the end. So it makes sure that you can collect the sample and bring it to the surface. Just a few pictures of the process. And we have here the example of how many samples and at which depth we collected them. In the gel push, we had some difficulties associated with precisely the gel condition, and in experience, it's because it's a brand new sampler, but in general, very successful in both samplers. And you see here where we have best results and a comparison at specific depth of the performance of the Thames and Moore and the gel push during the sampling process. So in the Thames and Moore, we have slightly higher recovery ratio, and there are a few that collect or collected just a few shorter samplers because of some particularities during the sampling. Then another important aspect is that we want to test this in the lab, and for that, all the processes in high quality sample are relevant to ensure that you don't disturb the sample until you test it. And it's not just the sampling process. So we were very careful about the transport, and for that we used specifically designed wooden boxes that were protected with some foam in order to make sure that the tubes wouldn't move during transportation. Let me remind you that Lisbon, or this area, very close to Lisbon, is about 3 hours drive from Porto, where we were going to do the tests. And then we wanted to make sure that the samples were carried and transported always in a vertical position as they were in the field, because if you leave it in the horizontal position and it's a loose sand, obviously it's going to create a void, and that would never recover the original structure. So following that, extrusion was also vertical, which is not so common. And you can see here an example of a collected sample that looks very sandy. And after this extrusion, which was executed immediately after sampling, we stored the samples in PVC liners to make sure that they were kept in temperature and humidity control conditions, and they were sealed to avoid any water content transfer. And you can see here different examples of the collected samples. Some you can see they look more clayey and others look more sandy. That's the very little bit that we got. And then in some cases you can actually see, but basically you can see that even in this small size sample, this height 140 millimeters height, you can see that there's some clay layers, or you can see some of that very smooth surface, which indicates the presence of clay, and then other areas which are rougher, like here, where it's definitely sandy. So in the end, we collected a considerable number of samples to study. And then I move to the laboratory test results. I have a video here, if you can play it, showing how handling is also important, not only these existing steps. So basically, after we've done the extrusion, we are going to take a sample from the PVC and see the sandy soil. there is a slit in the PVC tube from which we have to open to take the sample out. And it looks very loose. So we are in suspense until we put the membrane, and then we can continue with a lot more relaxed. So it's very challenging because obviously this is like a sandcastle. It looks like it's going to fall at any minute. And so after we did this, we wanted to check and assess the sampling quality that we were obtaining by comparing the shear wave velocities in the field to those that we obtained in the lab. And we did this in 2 stages. At bench test, so that is immediately after extrusion, and also in the cyclotraxyl test like you saw here. And as a reference, we use this sample quality classification that was developed during my PhD in Porto. And basically, this was developed for sands, or silty sand, so it's different from the classic clay sample quality evaluation. And basically, we're going to compare the normalized shear wave velocities, as I'll show later on. So we use the data from the geophysical in situ tests. In some cases, we have SCPTU. In other cases, we have SDMT. We have cross-hole. We have a variety of geophysical tests, and we compare them with Bender element tests in the laboratory. So after each sample was collected, you see here, it's exactly with the PVC tubes, we made the measurements in the bench, so at atmospheric pressure, in order to have an idea of how the stiffness of the soil was immediately after extrusion. And we also did the test with much more care and after reconstitution of the in situ stresses in the cyclotraxyl test and in any test that we did use samples. And you can see here an example of the measurement of the Bender elements using our procedure, which usually involves different frequencies, and we take the first arrival from the common point of the arrival of the shear wave. And this is very important. When you're comparing shear wave velocities in the field with those in the laboratory, you cannot do the comparison directly because there is a change in void ratio that we need to take into account. Otherwise, the comparison may be invalid. So when we have an in situ condition and we extrude the sample to the surface, we have a change in effective stress, and we need to account for that. And after sampling, you can see here that the sample is moved somewhere here. When we load it in the laboratory to the in situ condition, then we get to here, right? So we need the correction for the void ratio that occurs during the procedure, and also for the effects of the change in the shear stresses, of the effective stress in the case of the bench test. So these 2 corrections are fundamental, and the normalization to account for these effects is fundamental in order to do a correct and valid comparison. So following that, we do the analysis, and we found that we have the samples. They are predominantly of excellent or very good quality. But if we compare and look more closely at the open markers, you can see that the bench test always shows slightly lower results. And this has to do with the lack of confining pressure that's still affecting the measurement of the Bender elements. We get weaker signals and poor resolution, but also the effects of the reconstitution and reestablishment of the in situ stresses. And this involves not only the stress conditions, but also the full saturation. And full saturation is very important to us, especially if we're going to do liquefaction analysis, And that process, which I'm not going to discuss here, is only assumed complete full saturation when we have a p value above 0.98, and we always measure p wave velocity, and it should be around 1500 meters per second. After the undisturbed samples testing, we prepared with the same soil, we prepared reconstituted specimens to see how this compared with the undisturbed sample. And to do that, we prepared the undisturbed soil specimen either by moist tamping or air fluviation. We found that moist tamping was more suitable for to ensure the right relative density that we had on the undisturbed samples. And this was important to eliminate the variability and the dispersion of results. We obviously tested them at the same stress conditions and using the same cyclic loading conditions, which were determined from the design values that apply to that specific site. And here we have some examples. And what happens is that the undisturbed samples always have a different fines content, so a slightly different grain size distribution curve. So when we are doing the tests, I'm going to show you here examples of 3 undisturbed and the respective reconstituted specimen. And the results are different because the fines content of each of these specimens are different. So we have, in this case, 6%, where the reconstituted specimen has a slightly higher liquefaction resistance, cyclic resistance. Then here we have the case for a fines content of 9%, where we see that the reconstituted specimen has clearly a lower cyclic resistance, and the same happens for a slightly higher fines content of 18%. And this was analyzed for a large number of specimens, and we also did studies on the pore pressure ratio evolution. This is just a very quick view to show that in some cases we have a very similar response. So in terms of the number of cycles and the evolution of the pore pressure, and in other cases we have a very distinct result from the undisturbed to the reconstituted specimen. And this brings us back to the things that we cannot control and reconstitute in the laboratory, which is the natural fabric and structure of the specimen, especially in the case of interlayering or interbedding that we observed here, and in some cases more than others. Typically, when we have a higher fines content, we have more layering, and lower fines content, we have a more homogeneous specimen. And here are the results of some of the tests where we compare the shear wave velocity normalized by the void ratio function for the undisturbed, the reconstituted specimens, and we see a nice here we can see that the distribution is quite acceptable. That means that the samples can be considered similar. And in here on the right hand side, we can see that the results show that for very low fines content, we have the reconstituted specimen providing a slightly higher liquefaction resistance than the undisturbed ones. And the situation is reversed for higher fines content. And this leaves us with the main challenge that I want to bring to the floor today, which is how relevant it is or how important it is for us to collect undisturbed specimen samples and these high quality samples that are so hard and expensive to obtain in comparison with the reconstituted specimens. And I'll show this in my conclusions, but it's something that we need to consider. So basically our site investigation, we did a lot of site recognition, identified the type of soils, and it was very clear that we had large and big liquefiable layers which were useful for collecting these samples. And it was very important for us to look at the fines content even for the analysis of liquefaction susceptibility in terms of the field tests. Then we did the sampling stage, and we collected the samples from 3 different samplers. The ones here didn't perform so well, and I didn't go into details on the sampling quality because it wasn't the main topic, but the most advanced samplers proved to be the best, and they were able to reduce significantly the sample disturbance during sampling and induce minimal damage in the fabric. Obviously, the other stages of transport preparation are also very important to get these high quality specimens for testing. The Dames and Moore had a slightly better performance than the gel push sampler because it has a shorter liner, it's only 15 centimeters, and the other one is 1 meter long. And also by the generation of the vacuum with the neoprene seal, and that justifies a higher recovery ratio for this sampler. The immediate bench relevant tests compared against the cyclic seal tests shows some discrepancies, and these are attributed to the need to reestablish the in situ conditions. So even though it's nice to have shear wave velocity data immediately after sampling, is much more relevant to run the test even if it has some time effects in order to reestablish the stress state and to have the soil fully saturated as it is expected to be in the field in order to have more reliable measurements. In terms of the liquefaction assessment that we are focusing here, the undisturbed samples were tested, and then we were compared with the reconstituted specimen at the closest possible condition, that is with the same soil, a similar relative density, and with the same applied loading, so that these differences can be directly applied to the fabric and the structure of the specimen. But given this alluvial nature of these soils, we know and we could observe that the undisturbed samples has layering, interbedded layering, and this varied between the silty sands and the silty clays. And this made each individual undisturbed sample a unique soil with naturally different interesting properties. So this means that we cannot establish a constitutive model based on a unique sample, and we cannot characterize it and extrapolate from that. So since this natural interlayering cannot be adequately reproduced in reconstituted conditions, we observe these differences not only in terms of the cyclic resistance, but also on the cyclic strength and the buildup of excess work pressure. And the key parameter we found to be the fines content. So this really affected the comparison between the undisturbed and reconstituted. So for very low fines content, we have reconstituted specimens with slightly higher resistance, but predominantly the response of the undisturbed samples was higher and more stable. And this behavior obviously is attributed to the layering. I mean, the clay samples are, the clay layers are reducing the possibility of the excess pressure buildup, and that contributes very significantly to a more stable response, a smoother evolution towards liquefaction. And in our opinion, the undisturbed samples are valuable, obviously, for accurate characterization of the soil profiles, for identification of the materials, but in order to have representative constitutive parameters, we can only do that by doing the reconstituted specimen testing. So while those the undisturbed samples are very valuable, it is important to run more extensive tests in reconstituted conditions. And I wanted to make this short, so there are a number of references that you can look up after the conference, after this lecture, if you're interested. And this work was developed in collaboration with Professor Antonio Viana da Fonseca, who is the head of our laboratory, and some students, some finished and some who are ongoing, and also the technicians on our lab without whom we could have done this job. So thank you also to these companies that were associated with the projects that we had. And before I finish, I'd like to invite you all to come to Porto in about a year when we'll have IS Porto, which is the official symposium of the TC101. And we are now in the stage of paper submission, but you can always come even without paper if you like. So thank you.
Thank you very much, Cristiana. Unless there is a burning question, but I guess we can ask Cristiana. I have questions, but I will catch up with you later. We should perhaps close the session.
Okay, so I would like to invite Head of Department of Civil Engineering of European University of Lefke, Professor Ibrahim Bay, to present our certificate of appreciation to Cristiana. Before actually closing the session,